All right, and now we have Chang Liu from Hawaii University on Verbatim machine learning model manifestation in manageable neighborhoods. Chang, the floor is yours. Uh, Looking forward
Thank
to
you,
it.
Luis. This work is a collaboration with for my PhD students, Xianrong, Fan Hao, Zhongwen, and Cricket. Let me forward my slide. All right. So we all know that deep learning networks, machine learning are everywhere. That's the reason we are all here. It's used in safety critical systems, mission critical systems where things matter. But the black box nature of these deep learning models raise technical and ethical concerns when these are used in safety critical systems. Now, when I say it's black box, it's not necessarily just to AI researchers, because AI researchers, if you're really familiar with the model, if you handcrafted the model, you probably know more what's going on. But as for software engineers who's building a software on top of AI model or for users, these really are black box models, because how can you understand like 200,000 weights, right? That's difficult. Um, and then when we have built this system with the AI subcomponent as part of the system, there's a mismatch between the AI and the software engineering. Because in machine learning, researchers and the practitioners alike, they care about the overall accuracy and some other global metrics usually, right? And they consider individual outliers as acceptable norms. No machine learning model is going to be 100%, because that's just the way it is, because in nature it's more the statistics based underlying, right? It's not a causal relationship that we really figured out. So you are never going to reach 100%. Now, is 90% or 95% or 99% accuracy enough for AI researcher? Maybe there's a line that says, yeah, that's great. We don't care about one or two outlier cases or individual failures. And in some cases, in some applications, that may be okay, because see, we use Alexa, right? Sometimes you say, hey, Alexa, play a song. Hey, Alexa didn't get it right. And then you say it again. No big deal, right? So you have one failure case, but the most time it gets right. So it doesn't annoy you. If it's less than 50%, it probably become annoying. But if it gets right most of the time, that's fine. However, in software engineering, that's different. Once this component of AI subsystem gets built into a larger software or system that's treated as a traditional software system, then the software engineers, they care about user scenarios and the test cases. We consider high priority or mission critical bugs something that must be fixed, right? So if you have this image and it's classified, that's a bug. The bug needs to be solved. The bug must be resolved if it's a high priority one. And then we don't care about the 90% or 95% or 99% overall accuracy in this particular case, because we are dealing a particular bug. And increasingly, these systems are very can autonomous driving vehicle, for example, hit a biker in darkness? If someone justifies that says, it only occurs 1 in 1 million cases or 1 in 1 billion cases. No, if that's a test case that we need to resolve, we need to resolve it. So there's this big mismatch over here. And in our project, we try to build explanations so that the software engineers can start to understand what a AI model is working. And one way to do this is to help software engineers and the users alike to understand what's going on in an AI model by showing them a visualization of how the decision is made. Essentially, what the decision boundary is. So I'm not going to show you all these weights, millions of weights or tens of thousands of weights, but I show you what the boundary is with respect to your misclassification. So here in this diagram, for example, I'm trying to see my time remaining, and looks like I'm doing all right. So here in this diagram, the green 4 is a point of interest. It may be misclassified as a 9 or something, right? And then I would generate, using a technique to generate all these other 4s that look similar, but they change in a way that people can detect. We call these semantic changes. They have semantics that people can understand. And then we generate this neighborhood, and then we visualize the decision boundary. Then a software engineer look at that and like, oh, I see, that's why it's long. Then perhaps they decide you need to change your training data, you need to change your model, you need to do whatever change that you change that you need to make. Here is a different example, the boots and the sandals. Then here is yet another different example of fans with chairs, right? So you have chairs on the top bottom right corner, and you have fans on top. What if a chair on the bottom left corner is misclassified as a fan? Initially, you may be like, I have no idea why is this going on. But if we can generate enough examples to show you that it's actually the base of the chair that looks like a fan that mislead you into that, then perhaps you will find it more acceptable. You understand the system behavior. So in our proposed framework, we have 3 steps, 3 stages. One, we generated the neighborhood for human to come in and tell us whether or not it's good. The neighborhood is generated based on a given sample, typically a misclassified example. Then we perform classification. We classify all the misinterpreted, all the generated examples, try to visualize the boundary. Then we involve human in make these decisions so that the example generated it makes best sense to human. So here's the example. We have a 4 that could be misclassified as a 9. And we use VAE, valuation autoencoder, and they're underlying like 10 different dimensions. And then we generate it across every dimensions, right, differences. And a human is gonna, then we classify these, right? The orange is 4 and the blue is 9. And then we ask few humans to tell us what is meaningful to them. And then a human would select a few dimensions. Then we generate the entire neighborhood. Again, we involve human in identify the steps. And with that, people can finally understand that, oh, okay, so the top opening matters and this like horizontal thing that sticks out matters.